Well, thanks, Mr. Lapido. I'm Jan Bohlen from EDAG Engineering. I was employed there as a project leader in the defense sector. And defense sector obviously means, of course, civilian armored vehicles. This is the reason why we are here today, and we are very thankful to be here today to meet long-term business partners, long-term clients, old friends someday. And therefore, I'd like to present today a little about the comparison, about the loading conditions. So what can happen during a crash event and a blast event? Where are similarities, where are differences, and what does it mean when we try to understand civilian armored vehicles as a holistic approach? So usually, I'm talking about everything that comes right before the introduction to the market of a civilian armored vehicle. So body engineering, material, vehicle certification and testing, simulation obviously, since I'm a simulation guy, and of course manufacturing capabilities, how to get things done and how to bring the vehicle on the road. So basically anything how we as EDAG, as worldwide acting independent engineering service supplier, can help and support our customers the best we can all over the world. Of course, basically in Germany, and in total we have around 9,000 employees at this day, and our largest field where we grow at this moment obviously is the defense sector. But today, everything is a little bit different. Not trying to discuss the start of the life cycle of a vehicle today, but more the end, and especially the sudden end of a vehicle life cycle. So when it comes to an IED attack or a fatal crash event. So let's give you a little overview about my agenda for today. The introduction you already heard. And the next step, I'd like to compare crash loadings and blast loadings in common test scenarios. Afterwards, I'd like to go a step further in selected crash scenarios that might happen afterwards as a post-blast or post-crash consequences. Then I'd like to round up with a little material fatigue basics and associated crash potential that might be also fatal for the occupants in the end before I conclude my talk. So let's start with a comparison of crash and blast loading conditions. And here I'd like to first cut some or draw some boundaries. There are differences between crash scenarios, of course. And today I like to focus more on crash scenarios where you have a residual kinetic energy left. So not a classic full frontal crash where all the energy is gone afterwards. So the vehicle stands still, no kinetic energy that might be transferred into deformation energy afterwards, but more on the side crash or small overlap scenarios where you have a lot of kinetic energy left after the first incident. So a high potential for a secondary crash event. In this first part of the talk, just the moment when the action occurs is important. So just the loading conditions. Right the moment when the vehicle hits the target, so the second vehicle in this case, or the pressure wave interaction with the vehicle happens. Everything that comes later, so all the consequences, will be covered in the second part of the talk. What I like to compare is the NCAP crash test with a moving deformable barrier. It's a side crash test and the heaviest available crash test at this moment. It is driven with 1.9 tons of a deformable barrier crash wagon with 60 kilometers an hour. And I'd like to compare this with two different charges. Those different charges are on the one hand side the VPAM ERV 12.5 kilo PETN charge, and on the other hand side the Stanag 4569 15 kilogram TNT charge spherical. I have to do it, and I have to do the comparison to both of them, since obviously they are not equal, and I will explain that before I start with the crash comparison. It is right, both of the charges have an equivalent TNT mass of 15 kilogram. That's true, but when we take a closer look and we cut them in half, and we take a look at the ignition point of it, we clearly see that the characteristics of the charges are totally different. And when we do a little math on it, little geometric comparison, we see that there's an effective mass ratio of the explosive that is directed towards the target, in our case towards the vehicle, of 2.25 times. So in easy words, that means that the VPEM ERV 12.5 kilo PETN charge in cubic configuration ignited from the back is 2.25 times more severe to the civilian armored vehicle than the Stanag 15 kilogram TNT cube charge. Spherical charge, sorry. So it's a huge difference. I will come to that in a minute again. You ask yourself maybe how we create those values, those numbers, and also those kind of simulations where we gained those values of. We are using Impetus for this, which is a special developed tool for blast and ballistic simulation on the base of LS-Dyna. It gives us the opportunity to simulate several different materials, material cracking, the pressure wave interaction with target materials, so in the end, hand grenades, charges like I described before, and of course, different types of projectiles. And besides us, several different companies, especially in the defense sector, are using it. Spoken in the field of civilian armored vehicles, there are the three big players, the three OEMs of Germany, so Mercedes-Benz, Audi, and BMW, are using it to validate their products, to do a virtual evaluation according to the certification load cases prior to the real live fire tests. And since that's the case, they have the possibility in the end to save some prototypes there for the iterative process during the certification trials. And in this point, we are very proud that we were part of a project where we created the Primus breakable biofidelic dummy also as a simulation model. So this dummy is also available in the virtual world right now to do this virtual evaluation of the VPEM ERV Edition 3 also during the simulation phase. So, but now back to the charges again. I just told you the VPEM ERV 12.5 kilo PETN charge is 2.25 times heavier than the Stanag 4569 15 kilogram PNTE spherical and center ignited charge. And I'd like to prove that with some more parameters we gained from our simulations. Everything I said is gained from a detonation in a distance of 2 meters according to VPEM ERV. And all forces, pressure, and the impulse is gained on the passenger cell of the vehicle. So, spoken regarding the dynamic overpressure, we have a ratio of 7.3 between those two charges. The impulse, so in the end, the sum of all forces over the time is 1.7 times higher, and the force peak is around 2.4 times higher. That's nearly what this geometrical expression, so the effective mass ratio of 2.25 is equally. So in the end, we have to compare to both since they are far away from equal. And the vehicle that is protected according to Stanag 4569 with 15 kilogram spherical charge is not as protected as a vehicle that was tested according to VPEM ERV 12.5 kilo with a PETN. Next up to compare with is the crash scenario. As said, we are taking the NCAP crash scenario of 1.9 tons driven with a velocity of 60 kilometers an hour. That gives us a kinetic energy that has to be transferred and transformed into deformation energy of around 87 kilojoule, since around 1/3 of this kinetic energy of the deformable area is later on transferred to the vehicle and in the construction of the vehicle. And if we now try to get anything together, comes to this slide. And it's a little bit confusing, but I try to explain it the best I can. The blue lines are the side crash scenario. Red and green are Stanag and ERV charge. And what we can clearly see when we take a look on the impulse curve, for example, is that the impulse in the crash event is way higher than in a side blast event, but also the time frame is way longer. And then when we take a look on the force curve below, we can clearly see on the charges, so the Stanag charge and the ERV charge, the vehicle more faces kind of a punch in the blink of an eye, so it's directly over. You have extreme forces in no amount of time, where on the other hand side, spoken on the side crash, you have a waving force curve over the time, since the materials can answer to the loading. They have time to respond in their way. They have time to redistribute the forces, the loadings in the structure. And this is what makes a total difference here, and I will come to that right now, since I hope all of you know classic stress strain curves. They come with every data sheet of any material, but those data is gained from quasi-static testing. And quasi-static is, like the name says, slow, 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 slow. If you increase the speed, the material will behave totally different. Usually, armored steels get more brittle if you increase the strain rate. So in a crash regime, you have a lower elongation at break than in the quasi-static regime. And if you further increase it to ballistic or projectile impact regime, or even blast wave, it's also smaller. What comes also with it is the area below the stress strain curve. This area is proportional to the internal energy that the material can absorb before its point of failure. And if you increase the loading rate to a crash regime, for example, we can see that there is a fairly large area left, but it's of course way smaller than in the quasi-static regime. But if we increase the strain rate to a blast, for example, then the area gets smaller and smaller. So that's exactly what I say. During a crash, and therefore or even more during a blast, the material behavior gets more brittle and brittle. So therefore, different loading conditions that lead to different force time histories in the end lead to totally different energies that are acting on the vehicle, and therefore a totally different system answer. If we take a closer look in the comparison to the different parameters, we can clearly see none of them are equal. None of them are close to equal. So therefore, the statement on the first part of the talk is clear. Crash security and blast protection had to be considered independently. They are not the same, and or spoken from a holistic point of view, it's not valid to say, I have a blast protected vehicle that must be also crash protected. It's not. It's not valid to say that. Now, I'd like to come to the next part and move away from the blast loading to the consequences. So what happens after the first incident? And I will do that on selected crash scenarios that are quite common. And those crash scenarios, we have to look at them as secondary post-blast or post-crash consequences. So what can happen after the first incident? Since normally you're not standing still, you're driving your vehicle with 50 miles an hour or something like this, and then an incident happens. So, but then during the incident, not all of the kinetic energy is absorbed, and you have some energy left that has to be transformed or absorbed somewhere else during a secondary crash, for example. And this is what we face quite often. What do we see here? Of course, a classic rollover situation, since these vehicles have a very high center of gravity. Often we see improper driving, questionable vehicle constitutions, questionable road constitutions, maybe questionable mindset of the driver as well. And crashes like this leads to very high rotational energies. And the problem with those energies is that they have a inverted force direction. The vehicles are not designed according to this, since normally all the loads came from the outside to the inside, from side crash or, in our case, an IED explosion, and everything acts from the outside to the inside. But in crashes like this is totally different. I will show a video in a minute for that. So now, let's take a look what happens if we crash a non-armored vehicle in a scenario like this. What do we often see? All airbags are inflated, so all of them. Curtain airbag, side airbag, front airbag, everything is inflated, since the loading direction changes all the time. And we see that we have often a closed passenger compartment, maybe small openings, but the cell itself is still intact. This is what happens when no safety features are taken. You have a rollover crash where no belts are attached, no airbags are deployed, and even the windows were opened. So we have the possibility that the occupants can be freely ejected from the inside to the outside. This is the video from a different perspective. And what do we have to prevent that those things cannot happen? And the first, of course, we have to prevent the loss of structural integrity. That means that we have to use special hinges, a special body engineering and design process for the doors, for all the connections, and especially for the connection between the window frame and the door itself, since that's always the weak spot where we see failure in the end. Next up, it's quite obvious. We are a seatbelt all the time, minimize the contact or the contact possibility to the very hard, very rigid structure. And last but not least, don't change belt mounts or remove the belt retraction system, since this further minimizes the chance of any contact with the structure itself. Now, it's time to speak about airbags. Airbags are obviously a critical part of the safety structure and therefore also the passenger and occupant safety strategy of any OEM. On the top right, we see the airbag strategy of Toyota on its Land Cruiser 200, whereas on the right-hand side, the LC300 is presented. We see they didn't change anything. They changed maybe the shape of the airbags, but not the number of them. They are located still in the same places. We have front airbags, side airbags, curtain airbag, everything's still in place. And especially the curtain airbag is the airbag I like to talk about, since when we are speaking about a side crash scenario, this is what really counts, the side airbag and the curtain airbag, since it has the ability to prevent the contact of the head with the rigid structure of the safety glass on the side, and also minimizes the bending on the head regarding any neck injuries. But what do we see if we investigate armored vehicles after a rollover crash? Failed door hinges, and of course also door locks, lost front and side windows, broken or totally lost window frames, and of course destroyed door bodies, and last but not least, that not all available airbags from the OEM vehicle are deployed. And what's the reason for that? The reason is fairly simple. During the conversion process, to make space for the armor, most manufacturers just spare the curtain airbag. They remove it, and of course, therefore, the crash and occupant safety strategy of the OEM vehicle is, of course, compromised. The vehicle will act totally different, and that means a huge danger for the occupant in the end. Since, let's make little mind game here. Let's imagine we have both of the airbags attached. We have a crash from the side. Our body wants to move against, or relatively, against the side wall of the vehicle regarding our mass of inertia. So we have the possibility to lean on the side bag and then lean on the pillow to prevent the contact with the rigid structure. And usually the seats, and therefore also the airbags, remain unchanged during the conversion process. So the seat is removed and then goes back into the vehicle. That means that the side bag is still in place, but the curtain airbag is not. And what does this mean? This leads to the fact that we have the ability to have support on the side of our body, on the torso, but not anymore on the head. So the impact that our head can make on the side window or on the window frame and the neck bending moment is even higher. And therefore, we have an increased chance of injuries due to the removal of this curtain airbag. Next example for rollover crash is a rollover crash followed, or a side impact, and then afterwards a rollover crash. And this is not only applicable to SUVs, so we have to be aware of this even if we create a sedan-like vehicle, like in this case. But this picture leads me to another topic, cargo and load securement. Since in the end, what is the benefit for me as an end user if I have a perfectly blast and ballistic protected vehicle that is also crash secure maybe, and then I drive, have an accident and get killed by my spare tire, by any spare parts or tools that I have in my cargo area, not secured. So that's also a huge issue, but I don't want to focus this in my talk today. In the end, there will always be crashes that are so brutal nobody can imagine, and nobody can think of it during the development process of a civilian armored vehicle. This crash is a little confusing maybe, since there are different sources in the internet for it. But my belief is that there were a shelling attack prior to a crash. So was some grenade shelling on it. We see the impacts on the side window here, and then maybe the vehicle was damaged. The driver lost control, hit a quite rigid barrier, and then we have a rollover crash afterwards. And we see the same damage modes or failure modes like I described earlier. So we have broken window frames, ejected front and side windows, and in the end that no curtain airbag was installed. But all other airbags that were installed were deployed. So my estimate on this is that the VIP or the executive in this crash had a very good chance to survive the initial attack. Since the impacts are very small, I guess there were no harm to the VIP. But the outcome of the crash was that the VIP or executive in the back died and the driver was severely injured. And this is what I like to tell or to say in this holistic approach. What I said before, crash security and blast protection had to be considered independently, but in consequence, they are equally important, since I have no benefit if I survive the first incident, the first fragment attack or IED blast, and then I die as a result of the crash anyway. There's no benefit for the end user in this case. This topic leads me to another insert here, which is future threats. Future threats, mainly, in our belief, will come from above. We can see it in Ukraine, we can see it in the Middle East every day. Deadly UAVs, which can be made of highly available, low-tech products that are fairly cheap. They can carry up to 5 kilograms of explosive. They can land directly on the top of your vehicle. And in comparison with that, conventional hand grenades contain 100 to 200 grams of explosive. So all of the grenades that are used in the VPAM standards, for example. So our estimate is, if we are taking countermeasures, we of course will increase the center of gravity, and therefore we have an increased risk of rollover crashes in the future if we adapt to that. And that leads to the fact that crash security and especially rollover protection and prevention will be even more important in the future. So this is a huge issue today, and it will be an even more threatful issue in the future. So now, leaving the rollover crashes and move into the small overlap crash scenario. The small overlap crash scenario often occurs on narrow roads at excessive speeds. You have a high residual energy or velocity left, since you have very low energy consumption during deformation. Mostly you slip off the barrier, for example, and then you have a high chance of losing the control of your vehicle. Since the chassis is damaged, you maybe lose a tire, and then you have a high residual energy and therefore a very high chance of another secondary crash or even rollover. And what we see here quite often in the conversion is engine bay or fender armoring. It's a good thing to protect the engine from ballistics, but spoken from a crash perspective, this is quite problematic, since in the end you change again the crash strategy of the OEM. You change the way the energy is consumed in the vehicle, and due to this rigidity of the parts, you have some block formation of these armoring components quite locally on the firewall of your vehicle, and that will lead to excessive forces on some local points, especially on the connection of the A-pillar and the firewall, and right behind that is the driver of the vehicle. So it's a huge threat in the end, and you may ask how to improve then. Maybe not to put the armor right in front of the A-pillar, but on the side of it, so that it can be sheared off during a crash, but not acting as a sword that might intrude the armored component, the armored compartment here. In the next point of my talk, I like to give some material fatigue basics. It's not very deep, and we heard about it already yesterday a little, but in the end, the mission environment is crucial. The mission environment and the loads of the vehicle. We can have material fatigue nearly on any part of the vehicle. That comes from a tire, to a suspension, even to the frame of the vehicle. So, and the question is always, is the mission environment we are moving in equally challenging or more challenging than the environment this vehicle was initially designed for? And now I'd like to go back a little to the stress-strain curve we spoke about earlier today. This is for a one-time loading cycle. So you can exactly apply this much of stress to the material one time till it fails. But what happens when we are applying forces several times, 100 times, 1,000 times, 100,000 of times, during vibrations that comes from the road, for example? Then we have something like this. It's called a Wöhler curve. It begins with also the ultimate tensile strength of the material, and then the load that the material is able to withstand decreases with a number of loading cycles. Make a little example on this. You have the mass of your vehicle, the OEM vehicle, and this mass leads to a certain amount of stresses and forces all over your vehicle. And with this amount of forces and loads, stresses, it is able to withstand a certain number of loading cycles, maybe 200,000 kilometers or something like this. But now when you increase the weight of your vehicle, you increase the mass, you increase also the stresses, and therefore, when you take a look at the diagram, you decrease the number of loading cycles the material can withstand. So therefore you have a dropping life cycle. So the conclusion is additional weight, of course, leads to a reduced life cycle duration if no countermeasures are taken. Countermeasures like special wheels, special hinges, etc. Another way to read this diagram is you have the OEM number of load cycles the vehicle is designed for, so that gives you a bearable load of any part. But if you increase the load cycles in the same amount of time due to a road condition that is more harsh, you have more vibrations over the same amount of kilometers, then of course you have a decreasing in the bearable loads. So usually, well, that means that your parts that you design and you break into or bring into as special parts here have to be even more durable, even more heavy, and of course this leads to shortened maintenance cycles, but we heard about that also yesterday. But I want to now bring some examples of material fatigue, and I guess the results that comes with it are quite obvious. So if your tire explodes, if the rim breaks, or if you lose the rim because of broken wheel studs or something, or if you have already a deflated tire and then the emergency run flat system fails, all of that can lead to fatal secondary accidents and the loss of life in the ultimate end. This is not only applicable to wheels, tires and rims, but also to chassis parts and any other part of the vehicle. But I think this is the most placative way to show it here. So the question is always, do the manufacturers have the ability to provide endurance tested and certified special parts that are qualified for the weight and the strength of their product in the end? And with that, I'd like to conclude. We did a little comparison today of crash and blast loading conditions, VPAM ERV charge and Stanag charge, so cube versus spherical charge, are far away from being the same. Crash security and blast protection are not equally, so you have to take a look on both of it independently, but they are equally important, since when we are talking about the holistic approach, we for sure have to take a look at any different discipline, from blast and ballistic protection to crash protection to maintenance to fleet management to driver training. Anything is equally important, since anything can be harmful to the occupant, to the executive, to the driver, to the end user of these vehicles, therefore have to be addressed in the development stage already. So, and with that, since I think I've talked enough for today, one last sentence. Anything is possible when it comes to special protection and civilian armored vehicles, but of course not all possibilities should be considered for purchasing here. And with that, I'd like to thank you for your attention and be happy to answer any of your questions.
Jan, thank you very, very much. He promised me that there's another three of his colleagues as smart as he is. So any technical and another four.
Yeah.
Wow. I'm decreasing the IQ here.
We brought the full team here.
Okay. So again, during the lunch break, during the coffee break and the lunch break, feel free to go and ask all of them more technically. Before, we do have 10 minutes for Q&A. I would just want to say, again, the main idea of this is to present that, especially for the end users here, if someone comes and if a supplier, no matter what, come and say, I did a 20 kilogram explosive test, okay, and he did only 12.5, you cannot compare that. That raises a red flag. As Jan showed, it's a matter of the ignition, it's a matter of the explosive, it's a matter of distance. Nothing is really comparable. So ask the questions. Don't go blind by a number that a manufacturer, no matter where, tells you. Okay, that's.
And maybe to add on that was Johnny just said, there is all the time the possibilities. If you are unsecure with what you see from the manufacturer, you can always ask the Beschussämter, for example, in Germany, if they can read the documentation of this test and tell you if they are valid or not. So that's you don't have to do it all by yourself, or you can also, of course, contact me. But so we are independent. We work with anybody together, or like Armoured Consulting. So they are options for you. That's what I want to say.
Okay, thank you, sir, and good morning, everyone. And this is Abdulaziz again from Yemen. And as we are end users for EVs, and as our colleague Yoni say that we are the people that who are living with the EVs, and today our topic it is about the body of the EV in general and the contents of the EV. I would like to know if what are the weakness points of any EV? Where are the parts that considered the weakness of any EV? That's all. Thank you.
It's a good question. Thanks for that. To say it in one word, connection points. Connection points like weld themes, screws, bolts, any parts where you have to transfer a lot of forces through a very small amount of material. So you have two plates welded together with a small weld seam. Of course, where will it be? It has to be separated right in the weld seam. So weld seams are always problematic, bolted connections. So, but if they are done right and you have a kind of a self-supporting structure that maybe, yeah, like the name says, supports itself if the loads come from a given direction, then also loads like this, like the blast charges and also the crash charges, are good to handle, since we know what we have to evaluate the vehicles against and what we have to design them against. And in this case, if there will be a question like this, and there is in any vehicle development stage, we are using simulation to evaluate exactly those problems. We have a simulation model for a protected vehicle, for example. On the one hand side, we have it in Impetus, the software I've shown, for the blast and ballistic evaluation, and on the other hand side, we have it in Elastiner for the crash evaluation, and the OEMs, for example, to both of it, and do also crash their vehicle in live crash events.
Thank you.
I hear you.
So for the blast attribution study that you presented at the beginning, have you also carried that out with a real-life blast scenario where sensors are used around the vehicle to show the difference between the two charges? And have you taken, for example, to the extent you can, a control, like a specific build from the manufacturer, and put the same two vehicles out there, right, as similar as they possibly can be, and carried out the blasts, the two separate blasts on the same bill, and been able to see the difference in effects on the same bill between the two blasts?
Two very, very good questions. Also, thanks for that. The first one, yes, we validated our simulations with several vehicles and in several occasions by now. But the problem with that is, in the end, the measuring technique at the test facility often, since you have, like I presented, such amount of force in so less time, and therefore obviously you have some measurement insecurities all the time happen. But in the end, yes, we validated our simulations. There is a very good material library when it comes to explosives in Impetus already. And then, of course, we did some fine-tuning on it. The second question is even more interesting, I guess. If you have two vehicles, I would love to do that, but no, nobody wants to supply us with exact two same vehicles at the moment, and we were, or have not the chance to do it, let's say it like this, but of course, I would love to do that.
I've got some cars you can dispose of if you're interested.
Yes?
Please keep them for next year's shooting range. At least one of them.
So I want to ask a question regarding side airbags. So OEMs spend millions and millions of dollars and lots of time developing a vehicle, and my understanding is the position of the side airbag is critical for its effectiveness in the crash scenario. So how would it be possible to maintain the side airbag in a different position because of the armor cell and still ensure that it would be effective?
Mhm. Wow, very deep, but perfect. Yes, that's exactly the point where the problems begin. Since you're totally right, they're spending millions and millions, and it's not only the position and the position of the seat and the weight of the person that are sitting inside the seat. The ECU adapts the inflagration process of the airbag during the crash. It happens in milliseconds. And yes, you're totally right. If we were able to, or if we are able to bring just the physical airbag back into the civilian armored vehicle afterwards, after the conversion process, of course, this might be not as effective and totally on point like in the OEM vehicle, but it will be still better than have it not installed. But yes, you're right. That is a huge problem. You have to go totally deep into the ECU system of the vehicle to change the program itself to adapt all the values. But prior to that, you have of course to do crash tests and crash simulations to get a feeling and an indication of the right values you have to put into it.
Thank you very much. And also, it's very difficult to get technical information from the manufacturers in most instances. Thank you.
Jan, thank you very much for your talks. One question, and even the conclusion you mentioned, of course, we have to remove the window airbag. I think we all have all the same problem. But you mentioned, this was very good visible here on the display, as long as the car has a side seat airbag, or the airbag inside the seat. Yeah? But, on the body side, you mentioned if you have removed the window airbag, but still you have the seat airbag. That could be, even get it more worse. So is this maybe the conclusion to remove the side airbag in the seats if you have no window airbag? Could it be a solution? Not the best one, of course.
That's at least an option what many manufacturers are doing. They are doing it, so they're not really removing it since the seat is not changed, but they are removing it virtually by locking it from the ECU. And spoken with some experts regarding injury criteria and occupant safety from a university. They said regarding neck injuries, for example, the chance would be higher to have a less severe head injury or neck injury if you remove both and not only the curtain airbag. But in the end, my personal belief is that could be only the second best option. The best option must always be, and that is, of course, our all game and also the aim of your company, to provide high-level civilian armored vehicles for the sake of human life in the end of an ID attack or a crash.
Thank you, Jan.